deep in the vastness of space, where darkness stretches beyond comprehension and stars flicker like distant candles. Something extraordinary has emerged from the data streams of our most sophisticated telescopes. Scientists have recently uncovered something that has left them questioning everything they thought they understood about interstellar visitors. This isn't just another update about a cosmic traveler passing through our solar system. No. This is something far more profound. Something that challenges the very foundations of what we believed possible. As we journey together through this mystery tonight, prepare yourself for revelations that seem to belong only in the realm of science fiction just weeks ago. Let's settle in, take a gentle breath, and explore what makes this discovery so unprecedented, so bewildering, that astronomers around the world are calling it one of the most significant findings of the decade. The object we've been watching, the interstellar visitor designated 3I Atlas, has revealed something in the latest data analysis that no one predicted. What makes this discovery truly remarkable is not just what the data shows, but what it implies about the nature of objects traveling through the cosmic void between stars. For months, scientists tracked this visitor, measuring its motion, analyzing its light, attempting to understand its composition and behavior. The early observations were puzzling enough, showing non-gravitational acceleration without visible outgassing. A mystery that kept researchers awake at night trying to find explanations. But as more data accumulated, as more powerful instruments turned their attention to this fading speck of light, patterns emerged that defied every model, every theory, every expectation based on decades of studying comets and asteroids. As we continue our exploration, we'll discover what these patterns reveal, and why they're forcing scientists to reconsider fundamental assumptions about interstellar space. Imagine looking at something you thought you understood completely, only to suddenly realize you were seeing just a tiny fraction of what was actually there. That's the feeling astronomers experienced when the new 3I Atlas data came through. What we're about to discover will amaze you, because this isn't just about one unusual object anymore. The implications extend far beyond this single visitor, reaching into questions about how matter behaves in the extreme environment between stars, about what kinds of processes might be occurring in the vast darkness we once thought was essentially empty, and about whether our understanding of interstellar objects needs to be completely rewritten. As we journey deeper into this mystery, we'll need to set aside our preconceptions, open our minds to possibilities that seem almost magical, and follow the evidence wherever it leads. No matter how strange the destination, let's take a moment to imagine the journey that led to this discovery. Picture teams of astronomers in observatories scattered across multiple continents, their telescopes pointed at the same fading point of light racing away from our sun. Each observation adding another data point, another measurement, another piece of a puzzle whose final picture no one could have anticipated. The work was painstaking, requiring precise calculations, careful calibration of instruments, and the kind of patience that defines modern astronomical research. But as the data accumulated over weeks and months, something began to emerge from the numbers. Patterns that shouldn't exist, behaviors that violated predictions, signatures in the light that suggested, well, we'll get to that. For now, just know that what they found has opened up entirely new questions about the cosmos we inhabit. The implications of this are staggering, because if what the data suggests is correct, then 3I Atlas isn't just an unusual interstellar object. It might represent an entirely new category of cosmic phenomena, something we had no theoretical framework to predict, something that exists in a state or condition we hadn't imagined possible. Scientists have recently uncovered something extraordinary in the way this object interacts with its environment, in the subtle signatures hidden in its reflected light, in measurements so precise they can detect changes smaller than the width of a human hair from millions of kilometers away. These measurements tell a story about extreme conditions, about physics operating at its limits, about a universe far more complex and surprising than we sometimes give it credit for. As we journey together through the details of this discovery, you might find yourself drifting between wonder and drowsiness. And that's perfectly natural. Let the rhythm of exploration carry you. Let your mind wander through the cosmic mysteries we're unraveling. Deep in the vastness of space, 3i Atlas continues its journey, unaware of the revolution in understanding it has sparked among the beings on that small blue world it passed so near to. The object itself is now far beyond easy observation, receding into the darkness. But the data it provided during its brief passage through our solar system will be studied for years, perhaps decades, as scientists work to fully understand its implications. What makes this discovery truly remarkable is how it reminds us that despite all our technology, all our knowledge, the universe still holds secrets that can surprise and amaze us. What we're about to discover will challenge you to think differently about the space between stars. Most people imagine interstellar space as a perfect vacuum, an absolute emptiness where nothing happens, where objects simply drift in straight lines for eternity. But the reality is far more interesting. The new data from 3i Atlas suggests that this visitor experienced, or is experiencing, something during its long journey through the galaxy that left signatures we're only now beginning to interpret. As we continue our exploration, we'll discover what those signatures might mean, what they tell us about conditions in interstellar space, and why this has implications not just for understanding wandering asteroids and comets, but for our broader understanding of how the galaxy works as a system. Let's prepare ourselves for a journey into territory where certainty gives way to possibility, where established science meets the frontier of discovery. The story of this breakthrough begins not with the latest observations, but with something scientists noticed in the archived data, measurements that had been taken weeks or even months earlier, but hadn't been fully analyzed until recently. What makes this discovery truly remarkable is that the key insights came from going back through old observations with new questions in mind, looking for patterns that the initial analysis had missed or dismissed as noise. This is how science often works. Not through sudden eureka moments, but through careful re-examination, through asking what-if questions that lead to new perspectives on familiar data. As we journey deeper into this mystery, we'll see how a small team of researchers noticed something odd in the light curves, something that didn't make sense given the prevailing theories about what 3i Atlas was supposed to be. That anomaly, that tiny irregularity in the data, became the thread that, when pulled, began to unravel our understanding of this object. Before we can fully appreciate what makes the new 3i Atlas data so revolutionary, we need to understand what astronomers expected to find. Scientists have recently uncovered something extraordinary about how wrong their predictions were. But those predictions were based on solid reasoning and decades of experience with comets and asteroids. Let's take a moment to revisit what we thought we knew about interstellar objects before this discovery turned everything upside down. When Oumuamua was discovered in 2017, it introduced us to the concept of interstellar visitors, objects from other solar systems passing through ours. Its unusual elongated shape and mysterious acceleration puzzled scientists, but didn't fundamentally challenge our understanding of what such objects could be. Then came Tui Borisov in 2019, which behaved exactly like a normal comet. reassuring astronomers that most interstellar objects would probably fit into familiar categories. The detection of 3I Atlas in early 2024 seemed at first to continue this pattern. The object showed signs of non-gravitational acceleration, suggesting it was outgassing like a comet, even though telescopes couldn't detect the typical signs of such activity. This was puzzling, certainly, but astronomers had developed several plausible explanations. Perhaps the object was venting gas we couldn't see, like nitrogen or carbon monoxide. Perhaps it had an unusual rotation that made the outgassing invisible from our viewing angle. Perhaps its surface was composed of materials that sublime in unexpected ways. As we continue our exploration, we'll discover how these reasonable explanations were all built on assumptions that seemed solid, until they weren't. The scientific foundation supporting these theories was sound, based on everything we knew about how icy bodies behave in space. But the universe, as it so often does, had other plans. Deep in the vastness of space, 3I Atlas was carrying secrets that would only reveal themselves through the most careful analysis of the most subtle signals. The initial observations captured the obvious features: the object's brightness, its position over time, its overall trajectory through the solar system. But hidden within that data, like a whisper beneath a conversation, were hints of something far stranger. The breakthrough came when researchers began analyzing not just the overall brightness of 3I Atlas, but tiny variations in that brightness over very short timescales. They were looking for the kind of flickering that might indicate rotation, or perhaps small jets of gas pulsing on and off. What they found instead was a pattern of variations that made no sense in the context of a simple rotating icy body. The implications of this are staggering, because those variations suggested something far more complex was happening. Let's take a moment to understand what kind of variations we're talking about. Imagine you're watching a distant lighthouse at night. The light appears to brighten and dim in a regular pattern as the beacon rotates. That's similar to what astronomers see when they observe a rotating asteroid. A predictable cycle of brightening and dimming as different parts of the surface reflect more or less sunlight toward Earth. But what if the lighthouse's light also showed tiny, irregular flickers superimposed on that regular pattern? What if those flickers seemed random at first, but, when analyzed carefully, revealed hidden periodicities, hidden rhythms that suggested something complex was happening? That's analogous to what researchers found in the 3I Atlas data. The object showed the expected brightness variations from rotation, but overlaid on that were subtle changes that followed different timescales, different patterns, different rules. What we're about to discover will amaze you, because when scientists ran the data through sophisticated analysis algorithms, when they filtered out the known effects and isolated these unusual variations, a picture emerged that nobody had predicted. The variations weren't random noise. They weren't instrumental artifacts. They were real signals coming from the object itself. Signatures of processes occurring on or within 3I Atlas that our models hadn't accounted for. As we journey together through the implications of this finding, we'll explore several possibilities that have been proposed to explain it. Some are extensions of known physics applied in unexpected ways. Others push the boundaries of what we think is possible in the extreme environment of interstellar space. And a few are so speculative that many scientists hesitate to even mention them publicly. Yet the data seems to point in directions that can't be easily dismissed. Scientists have recently uncovered something extraordinary in the spectroscopic data as well. The analysis of how 3I Atlas reflects different wavelengths of light. Early spectra showed a relatively featureless profile, suggesting either a very uniform composition or that the object was too faint to reveal detailed features. But when researchers combined multiple observations, stacking the data to improve the signal-to-noise ratio, faint absorption features began to appear. These weren't the absorption lines of water ice or carbon dioxide, or the other common materials found on comets. These were different. Some matched organic compounds, complex carbon-based molecules that suggested either a very rich primordial composition or, and this is where things get interesting, active chemistry occurring on the object's surface. As we continue our exploration, we'll discover why the idea of active chemistry on a frozen object hurtling through space seems impossible, and why the data keeps pointing toward it anyway. The timeline of discovery reads like a detective story. In late March 2024, the first hints of unusual behavior appeared in the data. A researcher at a European observatory noticed that 3I Atlas seemed slightly brighter than predicted on certain nights. At first, this was attributed to measurement uncertainty, the inevitable noise in astronomical observations. But when other observatories reported similar discrepancies, questions began to arise. By early April, a working group had formed to coordinate observations and share data. They developed protocols for measuring the object's brightness with maximum precision, using consistent methods across different telescopes, deep in the vastness of space. 3I Atlas continued its journey, oblivious to the scrutiny it was receiving from multiple instruments across an entire planet. By mid-April, the pattern was undeniable. The object was varying in brightness in ways that couldn't be explained by simple rotation or viewing geometry. The variations seemed to have multiple periodicities, as if several different processes were occurring simultaneously, each on its own timescale. What makes this discovery truly remarkable is that these patterns only became clear when researchers started looking at the data in new ways, applying analysis techniques borrowed from other fields like signal processing and even climatology. The human mind is remarkably good at seeing patterns, but sometimes those patterns are so subtle or so unexpected that we need mathematical tools to reveal them. As we journey deeper into this mystery, we'll explore what those patterns might mean, what physical processes could create such complex variations, and why some of the proposed explanations seem almost too strange to believe. The first major hypothesis that emerged was that 3I Atlas might not be a single solid object, but rather a loose collection of smaller pieces held together by weak gravity and perhaps ice acting as cement. Scientists call such objects rubble piles, and many asteroids in our solar system have this structure. The idea was that as 3I Atlas traveled through space, heating from the sun or other processes might be causing pieces to shift or separate slightly, changing how light reflected from the object. This could potentially explain some of the brightness variations. But the more researchers looked at the data through this lens, the less satisfactory the explanation became. The variations were too regular in some ways, too correlated with other observables to be simple structural changes. As we continue our exploration, we'll see how this hypothesis evolved and what ultimately led many researchers to look for different explanations. Let's take a moment to consider the alternative explanation that began gaining traction in May 2024. Several independent research groups, analyzing the data from different angles, began converging on a startling possibility. What if 3I Atlas was experiencing some form of surface activity that we'd never observed before? Not traditional cometary outgassing, but something more subtle, perhaps involving phase changes in unusual ices, or chemical reactions triggered by cosmic ray bombardment, or electrical phenomena in the dust and ice on the surface. The scientific foundation for such processes exists in theory. Laboratory experiments have shown that ices exposed to radiation can develop interesting properties. Electrical fields can build up in dusty environments. Complex chemistry can occur even at extremely low temperatures if the right conditions exist. But observing such processes on an actual object in space, especially one so far away, was thought to be beyond our current capabilities. What we're about to discover will challenge many assumptions about what's observable and what's not. The breakthrough came when a team of researchers combined the brightness variation data with the spectroscopic observations and with measurements of polarization. The orientation of light waves reflected from the object. Polarization is a subtle property that depends on the texture and composition of a surface and how light scatters from it. When all three types of data were analyzed together, a pattern emerged. The brightness variations correlated with slight changes in polarization. The spectroscopic features showed subtle shifts that matched certain periodicities in the brightness. And all of this suggested that the surface of 3I Atlas was not static, not frozen into a permanent state, but was actively changing, reconfiguring, responding to something in ways that left detectable signatures in the reflected light. The implications of this are staggering. Because if the surface is active, we need to understand what's driving that activity. The most conventional explanation is sunlight, or rather, the lack thereof. As 3I Atlas approached the sun and then receded, it experienced changes in temperature and radiation exposure. Even for an object that never got particularly close to the sun, by cometary standards, these changes could trigger processes in unusual ices. Some researchers propose that 3I Atlas might be covered in ices that exist in multiple phases, like water can be solid ice, liquid water, or water vapor. If the object contains ices of exotic materials like nitrogen or carbon monoxide, these could undergo phase transitions at temperatures where 3I Atlas was traveling. A phase transition, such as from one crystalline structure to another, could change how the surface reflects light without necessarily producing large amounts of gas that we would detect as a visible coma or tail. Scientists have recently uncovered something extraordinary when they modeled this scenario in detail. The math works. Phase transitions in exotic ices could produce the observed patterns of brightness variation. The spectroscopic features match laboratory spectra of certain organic ices undergoing structural changes. The polarization measurements are consistent with a surface texture that's slowly evolving. Everything fits, almost too neatly. But science demands skepticism, especially when a model fits data very well. Researchers began looking for alternative explanations, for ways to test whether the phase transition hypothesis was correct or whether something else might be happening. As we journey deeper into this mystery, we'll explore those alternative ideas, some of which push into territory that makes many scientists uncomfortable. Not because the ideas are necessarily wrong, but because they're so unexpected. Deep in the vastness of space, far from the sun's warmth, far from any obvious energy source, how could an object maintain active processes? This is the question that has driven much of the recent theoretical work. One intriguing possibility is that 3I Atlas isn't relying on external energy sources at all, but is instead releasing energy stored within its structure from its formation, or from its long journey through interstellar space. Cosmic rays, high-energy particles that permeate the galaxy, constantly bombard objects traveling through space. Over millions of years, this radiation can deposit significant energy into the material, breaking chemical bonds, creating reactive species, even altering the crystalline structure of ices and rocks. Normally, this energy dissipates as heat, radiated away into space. But what if some of it gets trapped? What if the structure of 3I Atlas allows energy to accumulate, perhaps in strained chemical bonds or in unusual metastable ice structures, that then releases slowly over time? Let's take a moment to understand this concept through an analogy. Imagine a spring that's been compressed and held in place for a very long time. It contains potential energy, waiting to be released. Now imagine that the mechanism holding it slowly degrades, and the spring begins to gradually, almost imperceptibly, extend. That's similar to what might be happening with stored energy in 3I Atlas. The object absorbed energy during its long journey through interstellar space. Now, as conditions change slightly during its passage through our solar system, that energy is being released in subtle ways, driving the surface activity we're observing. This hypothesis is speculative, certainly, but it's grounded in known physics. Materials can store energy in metastable states. The question is whether enough energy could be stored and whether the release rates could match what we're seeing. As we continue our exploration, we'll discover that the calculations suggest this is at least possible, which is both exciting and deeply puzzling. What makes this discovery truly remarkable is how it's forced scientists to collaborate across disciplines. Understanding 3I Atlas now requires expertise in ice physics, radiation chemistry, cosmic ray interactions, spectroscopy, photometry, orbital mechanics, and more. Researchers who normally work in separate communities, attending different conferences and publishing in different journals, are now talking to each other, sharing insights, building models that combine ideas from multiple fields. This is how science advances at the frontiers, not through lone geniuses having sudden insights, but through communities of experts gradually assembling pieces of understanding into coherent pictures. The implications extend far beyond one interstellar object. If 3I Atlas is showing us processes that occur commonly in interstellar space, then every comet and asteroid that escapes its home solar system might undergo similar transformations during its journey through the galaxy. The data also revealed something unexpected about the object's trajectory. When astronomers recalculated the orbit using all available observations, including the latest data points, they found that the non-gravitational acceleration was not constant over time. It varied, increasing and decreasing in ways that correlated with, you guessed it, the brightness variations. What we're about to discover will amaze you, because this correlation provides a crucial clue about what's happening. If the brightness changes, reflect surface activity, and if that surface activity also produces thrust, however slight, then we're seeing direct evidence of a feedback loop. Something drives activity on the surface. That activity changes how light reflects, which we see as brightness variations. But it also releases small amounts of material or redistributes mass, which produces the non-gravitational forces that alter the trajectory. The fact that all these effects are correlated, that they vary together, strongly supports the idea that they're different manifestations of the same underlying process. Scientists have recently uncovered something extraordinary when they tried to model this feedback system. The equations are complex, involving thermodynamics, radiation transfer, material science, and celestial mechanics all at once. But when solved, they produce behaviors remarkably similar to what's observed. The model predicts that an object with certain compositions, exposed to cosmic ray bombardment over long periods, would develop a surface layer with unusual properties. When heated even slightly by approaching a star, this layer would become active, undergoing phase transitions or releasing trapped volatiles in bursts. These bursts would be small, too small to produce visible tails like a normal comet, but large enough to create measurable thrust and to change the surface reflectivity. The activity would be self-limiting, meaning it couldn't run away exponentially, but would vary in complex patterns depending on the rotation of the object and the distribution of active regions on its surface. As we journey together through these technical details, you might feel your eyelids growing heavy, your thoughts drifting towards sleep. That's perfectly fine. Let the complexity wash over you like waves on a shore. The specifics matter less than the overall picture, the sense of wonder at discovering that the universe is more intricate than we imagined. Deep in the vastness of space, billions upon billions of objects drift between the stars. How many of them are like 3I Atlas, carrying signatures of processes we're only now beginning to understand? How many harbor secrets that we lack the tools to detect? As we continue our exploration, we'll consider what this means for the future of astronomy, for our ability to study the galaxy not just by looking at stars and planets, but by examining the material that flows between them. The implications for astrobiology, the study of life in the universe, are particularly intriguing. If interstellar objects can remain chemically active during their long journeys between stars, if they can harbor complex organic molecules that don't simply freeze into inert solids, then these objects might serve as vessels for transporting the building blocks of life across vast distances. This isn't the same as saying that living organisms could survive the journey. The radiation environment in interstellar space is harsh, and the timescales are enormous, but complex organic molecules, the precursors to life, might be more robust. And if these molecules are protected within the matrix of an object like 3I Atlas, if they're embedded in ices and rocks that shield them from some of the radiation, they might remain intact or even undergo interesting chemistry during the voyage. Let's take a moment to imagine what this could mean for the distribution of life's ingredients throughout the galaxy. The concept that life's building blocks might be distributed by interstellar objects isn't new. It's called panspermia, and it has a long and somewhat controversial history in science. What makes the 3I Atlas data relevant to this discussion is that it provides evidence for active processes on interstellar objects, processes that could potentially protect and even create complex molecules during transit. If the surface activity we're observing involves chemistry with organic compounds, if those compounds are being processed in ways that create increasing complexity, rather than breaking them down into simpler forms, then interstellar space might not be the sterile void we once imagined. It might be a place where interesting chemistry happens, where molecular complexity can increase, where the ingredients for life are forged not just in the vicinity of stars, but in the darkness between them. As we continue our exploration, we'll discover why this idea excites some researchers while making others deeply skeptical. What we're about to discover will challenge you to think about life in cosmic terms. On Earth, life emerged relatively quickly after conditions became favorable. The planet formed about 4.5 billion years ago, and evidence of life appears in rocks dating back at least 3.5 billion years, possibly earlier. This suggests that the transition from chemistry to biology might not be as improbable as we sometimes think. But for life to emerge, you need the right molecules in the right place under the right conditions. If interstellar objects can transport those molecules across the galaxy, if they can deliver them to young planets where conditions favor biology, then the universe might be more hospitable to life than we'd expect if every planet had to synthesize all its organic molecules from scratch. The new data from 3I Atlas doesn't prove this is happening, but it opens the possibility in ways that previous observations of interstellar objects didn't. Scientists have recently uncovered something extraordinary about the composition of the organic molecules detected in the 3I Atlas spectra. Some of them are what chemists call complex, meaning they have structures with multiple carbon atoms arranged in rings or chains, with various other atoms attached. These aren't just simple molecules like methane or carbon dioxide. They're the kinds of molecules that, in the right environment, could serve as building blocks for larger structures, including some of the molecules essential for life as we know it. Now, to be clear, detecting these molecules on 3I Atlas doesn't mean the object is alive or ever was alive. It means the object contains interesting chemistry. The question is where that chemistry came from and whether it evolved during the object's journey through interstellar space. As we journey deeper into this mystery, we'll explore the evidence for both possibilities. Deep in the vastness of space, organic molecules are actually quite common. We've detected them in interstellar clouds, in comets from our own solar system's Oort cloud, even in meteorites that have fallen to Earth. Carbon is the fourth most abundant element in the universe after hydrogen, helium, and oxygen. And carbon has a remarkable ability to form complex molecules, to bond with itself and other elements in diverse ways that create structures with interesting properties. So finding organic molecules on an interstellar object isn't surprising in itself. What's surprising about 3I Atlas is the specific molecules detected and the evidence that they might be changing over time. If the surface activity we're observing includes chemical reactions that are actively modifying these organics, that would be genuinely novel. It would suggest that interstellar objects aren't just passive carriers of molecules frozen since their formation, but active sites where chemistry continues even in the extreme cold and emptiness of interstellar space. The scientific foundation for chemistry at extremely low temperatures is actually well established in some contexts. Laboratory experiments have shown that certain reactions can occur in ices at temperatures just a few degrees above absolute zero, especially when the ices are exposed to radiation that provides energy to overcome activation barriers. Cosmic rays, ultraviolet light from distant stars. These can all drive chemistry even in environments that seem utterly inhospitable. What hasn't been clear until now is whether such chemistry occurs on real objects in space at rates that would be observable. The 3I Atlas data suggests it does. The spectroscopic features show signs of change when observations from different times are compared. The changes are subtle, requiring careful analysis to distinguish from noise. But multiple research groups analyzing the data independently have reached similar conclusions. Something about the organic molecules on 3I Atlas's surface is evolving, and that evolution appears to correlate with the brightness variations and the non-gravitational acceleration. Let's take a moment to consider what this means practically. If interstellar objects are sites of active chemistry, then the longer an object spends in interstellar space, the more its molecular composition might evolve. An object ejected from its home solar system millions of years ago would have a different chemistry than one ejected recently, even if they started with similar compositions. This adds a new dimension to studying interstellar visitors. We're not just sampling what other solar systems are made of. We're sampling what happens to that material during its journey through the galaxy. Each interstellar object becomes a laboratory experiment in cosmic chemistry, running for timescales we could never achieve on Earth. The implications are staggering for our understanding of how molecules evolve in space, how complexity can arise from simpler starting materials, and potentially how the prebiotic chemistry that led to life might have been influenced by the interstellar environment. What makes this discovery truly remarkable is how it connects to questions about Earth's own history. Our planet formed from a disk of dust and gas orbiting the young sun. That disk contained materials from the interstellar medium, enriched with elements forged in previous generations of stars. But it also likely contained some fraction of intact interstellar particles, little chunks of ice and organic matter that survived the incorporation into the solar nebula without being completely processed. When Earth formed and was subsequently bombarded by asteroids and comets during the late heavy bombardment period, some fraction of those impactors might have been interstellar in origin. This means Earth's inventory of organic molecules, the chemical starting point from which life emerged, might include contributions from interstellar space. The chemistry we're seeing on 3I Atlas might be similar to chemistry that occurred on the objects that seeded Earth billions of years ago. As we continue our exploration, we'll discover why this possibility is both humbling and inspiring. Scientists have recently uncovered something extraordinary when they compared the 3I Atlas spectra to the composition of the most primitive meteorites found on Earth. There are similarities, not perfect matches, but overlaps in the types of organic molecules present. This could be coincidence, after all. Carbon chemistry follows certain patterns dictated by physics and tends to produce similar molecules in different environments. But it could also be evidence of a deeper connection, a shared heritage linking the material in our solar system to the broader galactic environment. The question of how unique Earth is, how special the conditions that led to life might be, has been debated for centuries. The 3I Atlas data doesn't answer that question definitively, but it does suggest that the raw materials for life are being transported and potentially processed throughout the galaxy in ways we're only beginning to appreciate. The detection of these organic signatures on 3I Atlas required pushing observational techniques to their limits. Spectroscopy of a faint, fast-moving object far from the sun is challenging enough without trying to detect subtle absorption features from trace molecular species. The breakthrough came from using multiple telescopes simultaneously, combining their data to achieve signal-to-noise ratios that no single instrument could manage. This technique, called networked observation, represents the future of astronomy for studying transient phenomena like interstellar visitors. As we journey together through the technical details, imagine the coordination required. Teams on different continents working together in real time, scheduling observations around weather and instrument availability, processing data immediately to determine what follow-up observations are needed. It's a remarkable demonstration of what humans can achieve when we collaborate toward a common goal. Deep in the vastness of space, 3I Atlas has now moved beyond the range where detailed spectroscopy is possible. The object is simply too faint. The sunlight it reflects too dim to analyze for subtle molecular features. But the data collected during its passage through the inner solar system will be studied for years. Every research group working on interstellar objects has requested access to the data. Some want to apply new analysis techniques. Others want to compare 3I Atlas to future discoveries, looking for similarities and differences that might reveal patterns. A few are developing theoretical models trying to explain the observations, models that might predict what we'll find when the next interstellar visitor is detected. What makes this discovery truly remarkable is how it has energized an entire field of study, bringing together researchers from diverse specialties to tackle a problem that no single discipline could solve alone. The implications for technology and instrument design are significant. If the subtle signals from 3I Atlas are representative of what we'll find on other interstellar objects, then detecting and characterizing these visitors will require specific capabilities. We need wide-field survey telescopes that can spot faint moving objects early, giving us maximum time to study them before they fade from view. We need spectrographs optimized for faint targets, capable of high resolution and wide wavelength coverage to detect subtle molecular features. We need rapid response observing capabilities, the ability to schedule observations quickly when something interesting is discovered. And we need automated data processing pipelines that can identify patterns and anomalies in real time. Because by the time humans notice something unusual in manually processed data, the object might already be too far away for follow-up. Let's take a moment to consider what the next generation of astronomical facilities might reveal. The Vera C. Rubin Observatory, currently undergoing final testing, will revolutionize our ability to detect moving objects, including interstellar visitors. Its combination of large mirror, wide field of view, and rapid cadence means it could discover dozens or even hundreds of interstellar objects over its operational lifetime. Each one will be an opportunity to test the ideas developed from studying Oumuamua, 2I Borisov, and 3I Atlas. We'll be able to ask whether the unusual behaviors of 3I Atlas are common or rare. We'll discover whether there are categories of interstellar objects, perhaps corresponding to different formation environments or different journeys through the galaxy. As we continue our exploration, imagine the catalogs of the future, databases containing thousands of interstellar visitors, each one characterized with spectra, light curves, orbital data, each one a piece in the larger puzzle of galactic material exchange. What we're about to discover will amaze you, because the technology for studying interstellar objects doesn't stop with telescopes. Some researchers are proposing dedicated space missions to intercept these visitors, to study them up close with instruments that can't function in Earth's atmosphere or that require proximity to the target. The concept is challenging. Launching a spacecraft on short notice to rendezvous with a fast-moving object requires tremendous energy and precision. But it's not impossible. Studies have shown that with appropriate pre-positioning of spacecraft in strategic orbits, and with sufficiently powerful propulsion systems, intercepts could be achieved for some fraction of detected interstellar objects. The scientific payoff would be enormous. Direct measurements impossible from Earth, possibly even sample return bringing pieces of another solar system back to our planet for laboratory analysis. Scientists have recently uncovered something extraordinary when they calculated what kind of mission profiles might work. The key is early detection. If we spot an interstellar object when it's still far from the Sun, we have years to plan and execute an intercept mission. The spacecraft wouldn't need to match velocities with the object. That would require too much fuel. Instead, it would perform a fast flyby, perhaps at tens of kilometers per second relative velocity, taking measurements during the brief encounter. High-speed imaging could map the surface. Spectrometers could analyze composition without contamination from Earth's atmosphere. Mass spectrometers could sample gas and dust particles streaming off the object. Magnetometers could measure any magnetic fields, the data from such a flyby, lasting perhaps minutes of close approach, would vastly exceed what we can learn from Earth-based observation alone. As we journey deeper into this mystery, we'll explore whether humanity has the collective will to fund such missions, whether the scientific value justifies the cost. Deep in the vastness of space, future interstellar visitors are already en route to our solar system. They don't know we're waiting for them. They don't know that we've developed the capability to detect them and, potentially, to reach out and touch them as they pass. The history of astronomy has been a progression from passive observation to active exploration. We moved from looking at planets through telescopes to sending robots to land on them. We moved from detecting asteroids to visiting them and returning samples. The next logical step is extending that capability to interstellar visitors. 3i Atlas might not be the object we send a mission to. It's already too far and moving too fast. But it has shown us what to look for. It has demonstrated that interstellar objects have stories to tell. Stories that we can only fully read through close-up study. The data revolution in astronomy is another key factor. Modern telescopes generate enormous amounts of data, far more than humans can analyze manually. Automated pipelines, machine learning algorithms, and artificial intelligence are increasingly essential for extracting scientific insights from this flood of information. The 3i Atlas discovery relied heavily on such tools. The subtle patterns in the brightness variations, the faint spectroscopic features, the correlations between different observables, these emerged from algorithmic analysis of thousands of individual measurements. Human researchers guided the process, deciding what questions to ask and how to interpret the results. But the heavy lifting of processing data was done by computers. As we continue our exploration, we'll discover how this human-machine partnership is redefining what's possible in astronomy. Let's take a moment to reflect on how far we've come. Just a decade ago, the idea of routinely detecting interstellar objects was speculative. We knew they should exist in theory, but actually finding them seemed difficult to the point of impractical. Now, we've detected 3 in 7 years, and we expect that rate to increase dramatically as our survey capabilities improve. We've progressed from simply knowing these objects exist to studying their properties in detail, to discovering that they're more diverse and more interesting than we anticipated. What makes this progress truly remarkable is how quickly it's happening. The pace of discovery in astronomy has accelerated tremendously. Technologies that seemed cutting-edge a decade ago are now routine. Questions that seemed unanswerable are being tackled with new instruments and new methods. The study of interstellar objects is riding this wave of progress, advancing from a curiosity to an established subfield of astronomy in less than a decade. The global nature of this research is worth noting. The 3i Atlas discovery involved telescopes on multiple continents. Researchers from dozens of institutions, data shared freely across international borders. Science has always been somewhat international, but modern astronomy particularly so. No single country has a monopoly on telescopes or expertise. The best science happens when researchers collaborate, when they combine data sets and perspectives to achieve insights that none could reach alone. As we journey together through the story of 3i Atlas, we're also experiencing a story about human cooperation, about what we can achieve when we work toward common goals. In a world often divided by politics and ideology, astronomy remains a field where people from diverse backgrounds collaborate effectively, united by curiosity about the universe. Scientists have recently uncovered something extraordinary about the educational impact of discoveries like 3i Atlas. These findings capture public imagination in ways that routine astronomical observations often don't. An object from another solar system, traveling through ours, behaving mysteriously. It's the stuff of science fiction made real. This excitement translates into increased interest in science education, in careers in astronomy and physics, in funding for research. The societal return on investment in astronomy extends beyond the specific discoveries. It includes inspiring the next generation of scientists, developing technologies that find applications beyond astronomy, and contributing to humanity's understanding of our place in the cosmos. The 3i Atlas data might seem esoteric, might appear to have no practical application. But the same could have been said about much of fundamental physics a century ago. And that research led to technologies like transistors and lasers that now underpin modern civilization. Deep in the vastness of space, the universe continues its ancient processes, indifferent to whether we observe them or not. Stars form and die. Planets coalesce from dust. Objects are ejected from solar systems to wander the galaxy for eons. This has been happening for billions of years, long before Earth existed, long before life emerged to eventually evolve beings capable of wondering about it all. What makes the 3I Atlas discovery truly remarkable is that it represents a moment when human curiosity and capability aligned to capture a glimpse of these cosmic processes. We happen to have the right telescopes pointed in the right directions at the right times to detect this particular visitor. We happen to have developed the analytical tools to recognize that its behavior was unusual. And we happen to have a community of researchers willing to collaborate to understand what they were seeing. In all the universe, that moment of alignment, that spark of understanding, occurred here, on our world, in our time. As we move toward the closing thoughts on this remarkable discovery, let's reflect on what it means for the future. The 3I Atlas data has opened up new questions, revealed new mysteries, suggested new possibilities for what interstellar objects might be and what they might teach us. Future discoveries will build on this foundation. We'll detect more interstellar visitors. We'll develop better models for their behavior. We'll hopefully send spacecraft to study them up close. Each step forward will refine our understanding. We'll answer some questions while raising new ones. That's the nature of scientific progress. Not a linear march toward complete knowledge, but an ever-expanding exploration where each answer reveals new territories to investigate. As we continue our exploration, imagine what astronomers a century from now might think when they look back at these early decades of interstellar object study, at the primitive instruments we used, at the basic questions we were asking, at the sense of wonder we felt at each new discovery. Let's take a moment to appreciate the technology that made this discovery possible. The telescopes are marvels of engineering, precision optics and mechanics working at the limits of what's physically achievable. The detectors are even more impressive. Devices that can register individual photons, that can distinguish between different wavelengths of light with remarkable precision, that can operate for hours or days, capturing incredibly faint signals. The computers that process the data are handling calculations that would have been impossible just decades ago. And the networks that connect researchers around the world, allowing real-time collaboration and data sharing. These are infrastructure that previous generations of astronomers could only dream of. The 3I Atlas discovery is a testament to human ingenuity, to our ability to build tools that extend our senses and our reasoning to comprehend phenomena far beyond the scales of everyday experience. What we've learned from 3I Atlas goes beyond the specific facts about this one object. We've learned that interstellar space is more interesting than we thought, that objects traveling through it can remain active in ways we didn't predict, that the chemistry and physics operating in that environment are more complex than our models suggested. We've learned that we need to remain humble in the face of nature's complexity, that the universe will continue to surprise us if we're paying attention. We've learned that collaboration across disciplines and across borders enables discoveries that isolated efforts could never achieve. And we've learned that there's still so much to discover, that despite all our technology and knowledge, we're really just beginning to understand the cosmic environment we inhabit. As we journey together toward the end of this exploration, let these lessons settle gently in your mind, like snow falling on a quiet night, each insight a delicate flake adding to the accumulation of understanding. Scientists have recently uncovered something extraordinary in how this discovery has shifted perspectives within the research community. Before 3I Atlas, many astronomers viewed interstellar objects as interesting curiosities, but not central to major questions in astrophysics. Now, they're seen as key to understanding galactic material cycles, planetary system formation, and potentially even the distribution of life's building blocks throughout the galaxy. This shift in perspective opens new funding opportunities, attracts new researchers to the field, and ensures that when future interstellar visitors are detected, they'll receive the immediate attention and resources necessary for thorough study. The long-term impact of 3I Atlas might be less about what we learned from this specific object, and more about how it changed the trajectory of interstellar object research as a field. Deep in the vastness of space, 3I Atlas continues its journey outward, back toward the interstellar medium from which it came. It's now beyond the orbit of Jupiter, fading from view even for our most powerful telescopes. Within a few years, it will cross the heliopause, the boundary where the sun's influence gives way to the interstellar environment. And then it will travel, for thousands or millions of years, through the dark spaces between stars, perhaps eventually passing near another solar system where other beings might detect it and wonder at its properties. The object carries no message from us, no indication that it was observed and studied by an intelligent species during its brief pass through our cosmic neighborhood. But in a sense, it carries our questions with it, the mysteries we attempted to solve, the wonder we felt at its presence. As we continue our exploration, imagine that distant future encounter, another civilization detecting the same object, perhaps puzzling over the same questions we've been asking. What makes this discovery truly remarkable is not any single measurement or observation, but the overall picture it presents of a universe that's dynamic, interconnected, and full of processes we're only beginning to understand. Every object in space, from the smallest grain of dust to the largest galaxy, has a history. It came from somewhere, was shaped by forces and processes, and will eventually end up somewhere else, transformed by its journey. 3I Atlas's history includes formation in another solar system, billions of years ago, ejection into interstellar space through gravitational interactions, millions of years drifting through the galaxy, bombardment by cosmic rays, slow chemical evolution, and finally a brief passage through our solar system, where conscious beings noticed it and tried to understand it. That story, that arc from unknown origins to unknown destination, with a brief moment of observation in between, encapsulates something profound about existence in the cosmos. As we approach the conclusion of our journey through the 3I Atlas mystery, let's return to the human element. The scientists who study these objects aren't just dispassionate analyzers of data. They're people driven by curiosity, by the same wonder that causes children to stare up at the night sky and ask questions. They've dedicated their careers to understanding the cosmos, accepting that most questions will remain unanswered in their lifetimes, that each discovery raises new puzzles, that certainty is rare and ambiguity is common. Yet they persist, driven by the joy of discovery, by the satisfaction of understanding even small pieces of the vast cosmic puzzle. The 3I Atlas data represents thousands of hours of their time, late nights at telescopes, days staring at computer screens, endless discussions and debates. Behind every measurement, every spectrum, every analysis, are humans trying to make sense of the universe. As we journey together toward rest and sleep, Let's appreciate those efforts, that dedication to knowledge for its own sake. Let's take a moment to imagine the future of this field. In 10 years, we might have detected hundreds of interstellar objects. In 50 years, we might have sent spacecraft to study several up close. In a century, we might have technologies that allow us to capture and return samples from interstellar visitors, bringing pieces of other solar systems back to Earth for detailed analysis. Or perhaps the progress will be slower. Perhaps the challenges are greater than we anticipate. Either way, the journey continues. Each generation of astronomers builds on the work of their predecessors, adds new discoveries, develops new techniques, asks new questions. The 3I Atlas discovery is one step in that long journey, significant in its own right, but also part of a larger progression toward deeper understanding. As we continue our exploration, consider how your own life is part of similar journeys, how each day adds to your personal understanding, how questions answered lead to new questions, how mystery and wonder remain constant companions through all of existence. The philosophical implications of interstellar objects are worth contemplating as we drift toward sleep. These visitors remind us that we're not isolated, that our solar system is part of a larger whole, that matter and energy flow through the galaxy in vast cycles that dwarf human timescales. They challenge our notions of here and there, of ours and theirs, showing that these boundaries are porous and perhaps arbitrary. An atom in your body might have once been part of a star that exploded billions of years ago in a distant part of the galaxy. That atom traveled through space, was incorporated into the cloud that formed our sun, ended up on Earth, and eventually became part of you. In a very real sense, you're made of stardust, and some of that dust might have traveled interstellar distances before settling here. 3I Atlas is a visible reminder of these connections, a tangible object that links us to the broader cosmos. Scientists have recently uncovered something extraordinary in the patterns of public engagement with interstellar object discoveries. These stories resonate with people in ways that many other astronomical findings don't. Perhaps it's because interstellar visitors are accessible concepts. You don't need advanced degrees to understand the basic idea of an object from another solar system. Perhaps it's because they engage our sense of wonder, connecting to deep human desires to explore, to discover, to connect with something beyond our immediate environment. Whatever the reason, the public interest translates into support for science, into funding for research, into inspiration for young people considering careers in STEM fields. The legacy of 3I Atlas includes not just the scientific papers and the data in archives, but also the countless people who heard about this discovery and felt a spark of curiosity about the universe. Deep in the vastness of space, the universe is vast beyond human comprehension. There are more stars in the observable universe than grains of sand on all of Earth's beaches. Around many of those stars, planets orbit. And from many of those planetary systems, objects have been ejected into interstellar space, becoming wanderers like 3I Atlas. The total number of such objects in our galaxy alone might exceed the number of stars. Most will never be detected by anyone. Most will drift for billions of years through the darkness, eventually dispersing as gravitational perturbations pull them apart or as they collide with other objects. But a tiny fraction, an infinitesimally small percentage, pass close enough to other solar systems to be noticed. 3I Atlas was one of those, a cosmic lottery winner in terms of visibility. Fortunate enough to pass through a system where technology had advanced to the point of detection and study. What makes this discovery truly remarkable is how it fits into humanity's broader story of exploration and understanding. We started by wondering about lights in the sky. Over millennia, we learned those lights were other worlds, that we lived on a planet orbiting a star, that the stars themselves were distant suns. We discovered the vastness of space, the incredible distances between objects. We learned that the universe had a history, that it evolved over billions of years, and now we're learning that it's interconnected in ways we're only beginning to map, that objects travel between solar systems, that matter and perhaps even the seeds of life circulate through the galaxy. Each step in this progression expanded our perspective, dissolved boundaries we thought were fundamental. The 3I Atlas discovery is part of that ongoing expansion, a reminder that there are always new horizons to explore, new perspectives to gain. As we gently approach the end of our journey tonight, let's reflect on what we've discovered together. We've explored how new data from 3I Atlas revealed unexpected behaviors, surface activity that shouldn't exist according to standard models, correlations between brightness variations and non-gravitational acceleration that suggest complex processes. We've considered what this might mean, from exotic ice phase transitions to stored energy released during passage through the inner solar system. We've contemplated the broader implications for our understanding of interstellar space, for the possibility of chemistry occurring on objects during their long journeys, for the distribution of organic molecules throughout the galaxy. And we've placed this discovery in context, seeing it as part of humanity's ongoing exploration of the cosmos, as a collaboration between researchers worldwide, as an inspiration for future studies. Let's take a moment for one final reflection. The universe is under no obligation to make sense to us, the fact that we can understand any of it. That the laws of physics are consistent enough to allow predictions, that mathematics developed by humans accurately describes cosmic phenomena. This is itself remarkable and perhaps mysterious. Yet we persist in trying to understand, driven by curiosity that seems to be a fundamental part of human nature. The 3I Atlas mystery might never be completely solved. Perhaps we'll detect similar objects in the future that shed light on its behavior. Perhaps new theoretical work will provide satisfying explanations. Or perhaps it will remain a puzzle, one of those observations that don't quite fit, that remind us of the limits of our knowledge. Whatever the outcome, the effort to understand is worthwhile. The journey matters as much as the destination. Scientists have recently uncovered something extraordinary about how discoveries like this one change us. Not just the scientists directly involved, but all of us who hear about them and think about them. They expand our sense of what's possible. They remind us that we live in a universe far stranger and more wonderful than everyday experience suggests. They connect us to timescales and distances that dwarf human concerns, providing perspective on our place in the cosmos, and they demonstrate that curiosity, wonder, and the desire to understand are values worth cultivating, that they lead to progress and insight. As we journey together towards sleep, let these thoughts settle like a gentle blanket, warm and comforting, wrapping you in the knowledge that you're part of something vast and magnificent. Deep in the vastness of space, countless mysteries remain. 3I Atlas has revealed some, created others, and reminded us how much we have yet to learn. But that's not a cause for frustration or disappointment. It's a source of excitement, of motivation, of wonder. There will always be new discoveries. There will always be questions to ask. There will always be frontiers to explore. And as long as humans retain our curiosity, our willingness to look up at the sky and wonder, we'll continue making progress, continue learning, continue expanding our understanding. The story of 3i Atlas is just one chapter in this much longer story. A story that began when the first humans gazed at stars and continues now as spacecraft explore the solar system and telescopes peer into the deepest reaches of space. As your eyes grow heavy, as sleep approaches, let your mind wander through the cosmos one last time. Imagine 3i Atlas out there in the darkness, continuing its eternal journey. Imagine the other interstellar visitors that will pass through our solar system in years to come, each one carrying its own mysteries. Imagine the discoveries yet to be made, the questions yet to be answered, the wonders yet to be revealed. And know that you're part of this story, that by learning about these discoveries, by caring about them, by feeling wonder at the universe's complexity, you're participating in humanity's collective exploration of existence. Sleep well, knowing that the cosmos is vast and beautiful, full of mystery and wonder, and that tomorrow brings new opportunities to learn and discover. The universe awaits, patient and eternal, ready to reveal its secrets to those who ask with curiosity and wonder. Good night, and may your dreams carry you through the stars.